and I am using the German spelling here, Schwartz. Instead of just, some people omit that C, right, but Schwartz in German is definitely within SCH, right. So this is so this involves bounding what? E of xy, that very important quantity which in signal processing, as I said yesterday, is called correlation, as opposed to statistics where it is not called a correlation, is used for something else. Again, I remind you about that, but here anyway. So this is a bound on mod of E of xy. So what is this bound? How big can this be for two random variables x and y which have finite means and variances? In other words, you want when E of x squared and E of y squared are finite, right, or in terms of, let me put it like this, bound on this in terms of E of x squared and E of y squared. So we automatically assume that these are both finite. What is this bound? Does anyone recall off the top of the head? Have you seen this different version of this Cauchy-Schwarz in some other context? Have you taken a course of linear algebra? This E of xy actually behaves like an inner product, and in the vector space of random variables. Now that interpretation we do not have time to explore here in any great detail, but for those of you that have studied any linear algebra, right, you have what is called an inner product space, right, and you have the dot product two vectors. Is E of xy is exactly like that, right. So the statement is simple. This E of xy, actually I can say whole squared, is upper bounded by E of x squared into E of y squared. That is as simple as this. Clearly, if you want to take the square root of this, you will get the absolute value, and you, of course, you put a square root on the RHS. So this is a statement of the Cauchy-Schwartz inequality. A very similar kind of statement happens when x and y are vectors in n-dimensional space, right. So this would be the lengths of the two vectors, and this guy sort of measures the angle between the two vectors in some sense, right. So you have, do you recall that definition? There is a cos theta which is this divided by this or something. You may have actually that angle makes a hell of a lot of sense in 2 dimensions, right, and 3 dimensions also, where it is actually a physical angle, right. Anyway, so how do we derive this? It's actually the derivation is actually quite interesting because it talks about estimating y in terms of x. So let me say, give us quick proof of this. Consider this E of alpha x minus y whole square, this quantity. What is this quantity that we are trying to take an average of? This this function gxy, right? This is basically gxy. This alpha x minus y, you can view it as an estimation error, right? If you say alpha x is an estimate of y, a simple linear estimate, the simplest estimate you can think of, alpha x minus y becomes the error, or y minus alpha x becomes the error, and the square of that is a very standard quantity for minimization. So we want to minimize this to be minimized. How do we minimize this? By varying alpha. Choose some real number alpha. Now we did a very similar minimization last week. What minimization did we do? We minimized E of x minus a whole squared. There we are saying we pick some real number that best represents x in some average sense, and we found that the mean was the best number in that calculation. So here it is something similar, but now we are allowed to scale one random variable by alpha and then say, okay, look at that difference and the average value of that difference, how do we minimize this? So minimization itself is very highly trivial exercise because so we have min over alpha E of alpha x minus y whole squared is min of what is this alpha square E of alpha squared x squared minus 2 alpha xy plus y squared, which is the same as the min over alpha of alpha squared E x squared minus 2 alpha E xy plus E of y squared. And note that this minimum is always non-negative, it can never be negative. This quantity is non-negative for every possible value of alpha. So it is also obviously non-negative for the optimum value of alpha. So what is this optimum value of alpha? So to get this, it is a simple real valued minimization problem of one over one real variable, which is the simplest minimization problem anybody can ever attempt, right. All you have to do is differentiate and set. So what is alpha star? The optimum value of alpha is simply obtained by so it is simply E of xy divided by E of x squared, isn't it? Isn't it E of xy divided by E of x squared? This will, when you differentiate with respect to alpha, this will go away, this will give you just 2exy, you set it to 0, you get 2 and 2 will cancel and you get divided by E of x squared. Okay, now we substitute that value of alpha back in the minimization, and what do you get if you do that? Please do that while I erase this. This implies what? The minimum value of E of alpha x minus y whole squared equals, just simply substitute that value of alpha star. If you do that, you get, what will you get? Alpha squared is E of xy, some manipulation is required but can't be helped, E of xy whole squared divided by E of x squared squared into E of x squared, that is that first term. Right, the second term is minus 2 again E of xy whole squared divided by E of x squared, that is that second term. And then what is the third term? Luckily the third term is simply, what is the third term? There is no alpha there, so thankfully it will only be plus E of y squared, and this must be non-negative. So what do you get from this? Just simplify. This will cancel this, right? And then these two, wow, they become the same thing. So E of xy the whole squared, what becomes upper bounded by? What does it become upper bounded by? X squared into? That's it. So very general theorem which is of great importance in mathematics and occurs wherever you run into vector spaces which have an inner product. And it turns out that to tighten the two sides of this, right, you can, supposing x and y have very large means and so on, you can get a tighter version of this bound by considering, instead of just taking the raw xy, you consider some normalized xy, but okay, let us say we look at the mean subtracted xy. So right. Supposing this works fine when x is as usable as is when, let's say, both means are 0, but if when x has mean mx and y my, y the mean my, then what? Then you consider x1 or whatever as a mean subtracted versions. You define x minus mx and y minus my, and then apply this to x1 and y1 rather than x and y directly. So what do you get if you do that? Remember, whenever you subtract the mean and you do E of xy, you get what? What do you get from yesterday's class? You get the covariance. So the left side of this inequality becomes the covariance of mean of x and y squared. So you get covariance of x comma y the whole squared. Is it not? What do you get on the right side? Variance of x multiplied by variance of y. We have not made any extra assumption about x and y, right? If you say the E squared and A y squared are finite, variances have to be finite and means have to be finite. So existence of the variance always implies the existence of mean, right? So so you get this, and now I come to what is called correlation. What I discovered is called correlation in the statistics literature. It is basically the ratio of covariance to the sigma x sigma y. So how is this written in this inequality written in a better written, if you wish? It is written in terms of mod of covariance xy divided by sigma x sigma y is less than upper bounded by 1. Note that this is positive, denominator is positive. So you can, the mod applies only to the applies only to the numerator, and correlation in statistics is this quantity, is this rho xy, what we call what we can also call as some, if we don't want to call it as correlation, but we will call it as correlation coefficient, which seems to be again a term used in signal processing, but it's basically this rho xy is this covariance without the mod, covariance of xy divided by normalized by the variance, product of the variances. However, for this course, right, we will stick to EXY as correlation, right, and I don't want to change that because I've done, I again went back and searched through the DSP textbooks, and usage of correlation for just plain EXY is perfectly consistent with the other uses of the word correlation in signal processing, such as the correlation of two sequences and so on, right? And so this, okay, so therefore EXY for us is going to be the statistic, correlation of two random variables, whereas here when in the statistics, right, they just keep in mind that this is what is they call correlation, and this mod rho is always upper bounded by unity. You can write that either as a subscript or write it with brackets, doesn't matter, but we are not going to take a very heavy use of this, or maybe not, right, maybe we will find some use for it a little bit later on, but for now we just we'll write it like this, just mod rho subscript xy. Okay. The reason why this xy appears here in parentheses because cov is already a kind of an ungainly construction, right, with quasi English, quasi like var. So it's whenever you have something like this, it's better to continue in the same line in this fashion rather than putting subscripts. But since they stole this letter rho for this quantity, it's a single letter, so xy goes naturally as a subscript. So this mod rho less than 1 is also a statement of Cauchy-Schwartz, in other words. And as I said, we will just call it rho, I don't even want to give it any name actually, right, and rho equal to 0 is the same as covariance equal to 0, which is the same as x and y uncorrelated. So mod rho equal to 0 does not tell you that anything about x and y at all. It does not tell you how dependent they are or how independent they are. It turns out if x and y are independent, certainly rho will be 0, but the reverse, as we saw yesterday, is certainly not true. You can have extremely highly dependent y equal to x squared and still have mod rho equal to 0. On the other hand though, going back to this Cauchy-Schwarz, when do you get the limits, when do you get equality here? You get equality, there is a very strong linear dependency between x and y. Equality in Cauchy-Schwarz is also a very important thing. So supposing this is 0, that means in fact you are perfectly able to estimate y as a simple linear function of x. The error is 0. Remember, right, if the E of some z squared is 0, that means that z had better be 0 with almost with virtual certainty. If E of z squared is 0, right, z is almost surely equal to 0 with probability equal to 1. That is the statement of probability theory. So here if we say E of alpha x minus y whole square is equal to 0, then that means that alpha x equal to y with very high probability, or probability almost equal to 1. So what does that mean? And probability of alpha x equal to y is equal to 1. That is, this is what is called A dot S, right, almost surely, alpha x equal to y almost surely, that is the statement used. That means basically you have something like this, right, that y is more or less nothing but alpha x. But what does this rho by u on top of this, right? Supposing somebody says rho equals 1, well alpha can be negative also here, right? So I can have either negative or positive, right? It can be either this way or this way. Here if rho equal to plus 1, then that means basically you can go back and check, right? It means that the mean removed random variables are related by this alpha. So you can get basically some ax plus b type of relationship. That is, the ax plus b comes because of you have removed the mean here. So this line does not necessarily have to pass through the origin, it can be any straight line anywhere. So if rho equal to plus 1, that means that y equal to ax plus b, where a is positive, then they are positively correlated almost surely, of course. And rho is minus rho xy, I mean if rho is minus 1, that means what? The same ax plus b with a less than 0. So rho is a great indicator of a linear relationship.